continue our series on the basics and fundamentals and mathematical theorems and theories that will help any engineer, any biological student, any physics student, or any area of study to understand this and apply them appropriately. I'll be talking about logarithms. For the introduction, I will advise you to check the other parts, the other series, and other videos to help you follow up this properly. For logarithms, we discussed the rules, but I'm going to continue with the rules we discussed. One of the main rules that require the help of logarithm is the rule that has to do with the argument having a power. So if you have a logarithm given, you have a base, let's say the base is n, and the argument is having a power, let's say c, any power, any value. That will give us c log a, c to base n. So this is actually true, because you can actually prove that since you have log a raised to the power of c is the same thing as log a times a in c places, or c times. So this is log a times log a in c places. So this a raised to the power of c, like my indices class, was a times a times a times a in c places. And you know, by the first law of logarithm, this can be written as log a plus log a. We continue adding like that in c number of places. So by the first law of logarithm, we agree that log a plus log b is simply log a b. We agree this. So also the reverse, log a times b is log a plus log b. So log a plus log a plus log a is going to give us log the multiple of the log of the multiple of the argument. So, and this is going to add up to give you c number of log a. So that is how we view the proof of that. Very simple and very direct proof to that. So we know that this is going to give us the same thing. So that is a very beautiful rule. You can use that to tackle questions of this nature. Let's say this is equal to 8. We can actually use that principle to tackle this if we know the log of 8, we know the log of 2. This is actually a very simple question we can solve using indices. We know we can solve this. Remember, we can solve this having this. So also you can, this x is equal to 3 here by the first law of the law we discussed on indices. Here we can also have the log of 2 raised to the power of x equals to the log of 2 raised to the power of 3. So we can also have this. What I've done here is to write log and write log here, to apply that logarithm to both sides. So I write log this and log this. You can see this log this and also log this. And with this principle, we know that we are going to have this to be x log 2, and we're going to have this to be 3 log 2. So this is 3 log 2, and this is x log 2, and we know we can divide both sides by log 2. We can divide both sides by log 2 to have our answer to be x equals to 3. But this is actually a very simple case, as we may not have this case most of the time. We may have typical, very funny looking question like, let's say 3 raised to the power 8 equals to 2. So we may have something like this. We need the help of logarithms to be able to tackle a question like this. You may not be able to do this for this. So here we can have log 3 raised to the power of x equals to log 2. And we know very well that by this rule, this is going to give us x log 3 equals to log 2. We can divide both sides by log 3, and divide it by log 3, and we have this, the cancellation law, and have our answer to be 0.3010 divided by 0.477. Please, you can confirm these values using your log table. In your log table, log 2 is approximately 0.3010 and log 3 is approximately 0.4771. You can divide that into your calculator and have your answer for x. So all these exponential equations, these are called exponential equations, actually helps us to appreciate the laws of logarithm. This would have been so difficult and almost impossible if we don't apply these laws of logarithm. Although there are methods, there are advanced methods for solving this, like the Logarithms method and so on in calculus, but the logarithm method is quite a wonderful method we can also apply to solve it. Now, I'll round up my video by discussing another principle that is very, very important. Now, from what we've discussed, you see, we're talking about the argument having the power. So sometimes we can have the b is having the power. So this, in the other case, we discovered we were talking about log a is to the power of c. But in this case, we have the b is having the power and not the argument. The b is having the power. What we have in this case, this is going to give us 1 over c log a. That gives us 1 over c log a. And that can be easily proven by simply writing this in its index form. So that can be easily proven. I'm not going to the proof now. That is a proof. The proof is very obvious and simple from here. So it's good for you to note this, and we can use it to solve questions like this. Suppose we were given something of this nature, and to simplify this, this can give me log 8 can be written as 2 raised to the power of 3, and we still have 2 here. 8 is 2 raised to the power of 3, and by this rule, I can simply write this as 1 over 3 log 2, 2. So you see, instead of having this 3 here, I'm having this as the inverse of 1 over 3, the inverse of the power. So what we have is c, we have the inverse of the power 1 over c, what we have is 3, and we have the inverse of the power 1 over 3, and we have this. And you remember by my last video, I agreed that whenever you have a base and the argument to be equal, this will be equals to 1. So this is equals to 1 over 3, and all this is just 1. Recall that log a is equals to 1. So these are very beautiful mathematical principle that we can apply anytime, any day. So in my next video, I'm going to be talking about change of base, and I will I'll have a problem solving video where I will solve a lot of problems, and I'd like you to send challenges and problems to my email so we solve them, and we get a good result from all this. Thank you very much, and bye.